Alright, my name is deGruy. I'm with group 4, and I'm the lead for the bomb calorimeter experiment number 2. So the introduction, the power bomb calorimeter, it measures the amount of energy released by an explosion by observing the change in temperature of the water in which the explosion takes place. Components, it's an explosive sample that's inside this little crucible thing that's inside the bomb casing, that's placed in a bucket of water that's also within a shell, a calorimeter shell. It's got a thermocouple in it, in the water, and ignition wires going into the bomb casing that's in the sample also. There's a little diagram. This one's a little different from the one we're using because the one we're using, the bomb is actually inside a bucket of water that's inside the shell around it, not just sitting in a shell filled with water. Some objectives for this experiment: to become familiar with the physical principles, procedures, and analysis techniques associated with the oxygen bomb calorimeter, determine the thermal capacitance of the system, and determine the gross heat of combustion of the samples provided. So practical applications, basically anything that involves the burning of something or heat generation, anything like that. So digestion of foods, burning of fuels, anything similar to that. Some of the theory behind the calorimeter. Upon bomb ignition, the heat is transferred from the bomb to the water by conduction. The calorimeter device measures the heat of combustion by observing the rise in water temperature and then calculating the number of heat units that were liberated from the explosion. The basics of this experiment is the first law of thermodynamics, which is what you saw earlier when he presented on the first law of thermodynamics, but this is a derivation of that equation where the heat of combustion is equal to mass times the specific heat times the change in temperature. So apparatus and procedure, this is just the items that, all of the things that are listed out that we're using for this. So we have an igniter, the bomb, a laptop with PDAC view installed, the analog to digital converter, a water bucket, thermocouple, water stir motor, and associated parts. The bomb is made out of the bomb housing, and the bomb lid has attached to it the crucible and the different pressure valves necessary, and then a lid locking ring also. So preparation, we cut 10 centimeters of nichrome ignition wire, place no more than that much of a sample fuel into the crucible. You don't want to use any more than that because you don't want to damage the calorimeter, and that's also a safety concern. Connect the ignition wires to the bomb electrodes. And it's very important that the wire isn't grounded against the crucible and only touching the fuel, otherwise you will not achieve ignition of the fuel. It will just be grounded out. Add 1 milliliter of distilled water into the bottom of the bomb. No water in the crucible though, because that will also prevent ignition. Place the lid on the bomb vessel and hand tighten the locking cap, and don't disturb the fuel sample inside. So you have to do all this very slowly and carefully. You want to purge the bomb by alternately pressurizing and depressurizing. So you attach this regulator, and you're basically purging the air out of the bomb until the only thing that remains is just pure oxygen. You only want oxygen inside the bomb. Okay. Open the regulator, pressurize the bomb to 30 atmospheres. Don't overpressurize, as this may cause damage to the bomb when the fuel is ignited. Shut off the oxygen regulator valve, release the line pressure by pulling the back pressure relief valve. Remove the oxygen hose from the bomb cap. Depressurize the bomb by unscrewing the bomb pressure relief valve by 1 full turn. And then you repeat these steps until you think you have successfully purged the bomb and you're back at 30 atmospheres. The water jacket, you add 2 kilograms of water to the bucket and make sure that the water temperature is within 5 degrees above or below room temperature. You put the bucket in the calorimeter jacket, positioning it on the feet of the bottom of the jacket, and make sure that it's touching the ground button in the center. You want to open up the software to record the data on the computer, insert the thermocouple plug to the PDAC, and place the thermocouple in your palm to verify that it's reading correctly. And then put the thermocouple in the positioning bracket, calorimeter lid, and then you prep the data acquisition system. You want to consider that about 2 minutes of baseline data is going to be taken, followed by several more minutes of transient data. So you want to make sure that you set the right time constant for that. So you lower the bottom of the bucket of water. Actually, electrically, we kind of went over some of this. Check the continuity of the ignition circuit by using the multimeter. Set to those settings. Look for 0 ohms. Otherwise, the bomb will not ignite once again. Start the experiment, log your data, and after 2 minutes, press the ignition button to ignite the bomb fuel. If it ignites, there's going to be a light that lights up. If the light doesn't light up, you'll have to take it apart, alert the lab technician, and start over again. So after you finish taking all of your data, you save the data to the desktop in that format, and then repeat the experiment with the unknown fuel. For shutdown, just follow these directions. I listed everything. These estimates aren't really valid because I didn't misunderstood the lab manual's instructions. But I looked up, that's the heat of combustion for benzoic acid, and that's about what you'd get if you did it the way I looked it up. So that's it.